So in the last classes, we have discussed the importance of CAD-CAM in industry, role of computer in product development cycle, role of computer in product design, how CAD-CAM is gaining importance in the industry nowadays, what are different types of geometric modeling, how we can model the design and how we can analyze it, what are different techniques for geometric modeling. So now we'll go for geometric transformation. So what is transformation? Transformation is the change of any entity with respect to dimension, with respect to coordinate, with respect to a scale. So they are the transformation. So what is geometric transformation? So basic transformation is scaling, translation, rotation. So purpose of transformation is to move the position of the objects, to alter the shape of the objects, to change the orientation of the objects. So as we have studied earlier that geometric this computer design consists of three components, namely design, analysis, and visualization. So geometric modeling provides a mathematical description of geometric object, point, line, conic section, creation of curves. Then computer graphics provides a visual display of manipulation of objects like transformation of object, editing, pointing, printing. So different languages are there. So with the help of transformation, we can say that transformation is the backbone of the computer graphics, which enables us to manipulate the shape, size, and location of the object. It can be used to effect the following changes like change the location, change the shape, change the size, rotate, copy, generation of surface from a line, generation of solid from a surface, animate the object. So then we will go for two-dimensional transformation. So transformation may be two types, two-dimensional and three-dimensional also. So two-dimensional translation we will go. So two-dimensional transformation is the very applicable in the numerous applications like geometric modeling, manipulation of size, shape, location. So transformation is used to generate a surface also. So transformation with the modeling transformation and visual transformation. Modeling transformation alters the coordinate of the object. So basic operations are scaling, translation, rotation, and combination of one or more of these things. So for software purpose, we can use a scale command, move command, rotate command for transformation in the software. Visual transformation is the transformation in which there is no change in either the geometry or the coordinates, but a copy is only placed at different places where you have be required. So in AutoCAD, we require zoom command, pan command for visual transformation. So two-dimensional, we will go for translation first. So in translation, what happens? You have to move the object from one point to another. So it is one of the rigid body transformation which moves objects from one place to another without deformation. Only we can change the position. There is no deformation here. So translate the object by adding offset to the coordinate to generate new coordinate system. So let tx and ty be the translation distance. So in matrix format we had t the translation vector. So in for each transformation there is a matrix. So we have to this add or multiply this matrix to the original coordinate matrix. So to get the new transformed coordinates. So in translation, suppose tx with ty with the translation distance to which amount we can translate. So you can see x dash means new position of the x coordinate is the x plus tx. Then y dash is y plus ty. So t and tx and ty is the amount of distance by which translation is done. So in matrix format, t is the translation vector. So p dash is the new coordinate of the new point. So x dash y dash is the coordinate of the new point. So p is equal to x by the principal this original point, and t the translation vector. So p dash is equal to p plus t. So after translation, we get the final position of the point is p dash. So equal to p plus translation matrix. So in this diagram, you can see also p is the original, and after translation, the point is moved to p dash. In this diagram, you can see. So in two-dimensional transformation, we could translate the object by applying the equation to every point of any object, because each line in an object is made of an infinite set of points. However, this process would take an infinitely long time. So fortunately, we can translate all the points on a line by translating only the lines into points and drawing a new line between the endpoints. So the figure translates the house by 3 minus 4. So in the diagram, you can see left part is before translation and a right party after translation. So you can see the initial point of the object is 4-5 and 7-5. So we are translating this object by 3 comma minus 4. So by after using the translation matrix, we are getting the final point in the second diagram. So this is translation example. So basic two dimension geometry transformation. It comes rotation also. So rotation axis and angle are specified for rotation. So we are converting the coordinates into polar form for calculation. R angle theta. So the new position coordinates comes. So you can see we convert the Cartesian into polar in the form x is equal to r cos phi, y equal to y sin phi. For example, to rotate an object with an angle, this is the new position comes x is equal to r cos phi plus theta equal to r cos phi cos theta minus r sin phi sin theta is equal to x cos phi x cos theta minus y sin theta. So y dash equal to this r sin phi plus theta equal to r cos phi sin phi plus r sin phi theta minus r sin theta plus y cos theta. So in matrix format, in polar form, we can see rotation is cos. This is the matrix rotation matrix cos theta minus sin theta cos theta. So for normal new point is a p dash equal to r into p. So rotation what point x r by r. We can get x dash equal to x r plus x minus x r cos theta minus y r sin theta. So similarly, we can get coordinate for y dash. So you can see there before rotation this object is showing in first diagram. After rotation this we seeing looking like this. So you can see we can rotate the this is an example of house. We can rotate the house by 45 degree. So after rotation this house will look like this. So this is the normal rotation. So positive angles are measured counterclockwise from x towards y. For negative angles you can see use identity like this sign. So this is the rotation example. So basic two-dimensional geometry transformation is a scaling also. So scaling means to alter the size of an object by multiplying the coordinates with a scaling factor xx and xy. So scaling means we have to this scale the object by some factor. So a scaling factor in x direction is sx and a scaling factor in y direction is sy. So to change the size of an object by multiplying these coordinates with a scaling factor, we will get the uh, transformed coordinates of the object. So in matrix format, is here S is 8 2 by 2 a scaling matrix means we are changing the this scale factor by 2 only in both direction x and y also. So we can change it also. So choosing a fixed point as its centroid to perform a scaling. So x dash equal to x into sx. So x dash is the coordinate of the new point, x coordinate. So x is the original coordinate point and sx is the scaling factor. Similarly, y dash equal to y into sy. So in matrix format where S is 2 by 2, so x dash y dash equal to sx and sy scaling factor, then we are putting 0 as equal to form the identity matrix into xy. So choosing a fixed point, we will get x dash equal to x into sx plus xf into 1 minus sx, y dash equal to y into sy plus yf into 1 minus sy. So you can see this diagram of the scaling. So this is first diagram is showing the original coordinate point of the object 4 5 and 6 7 5. This is, and we are getting the scaling transformation. So after this you can see that this size of the object is very small. So we have a new coordinate is 2 comma 5 by 4 7 by 2 comma 5 by 4. So we have scaled it by using the scaling factor and scaling matrix. So in this figure the house is scaled by 1 by 2 in x and 1 by 4 in y. So scaling is about the origin here only. You can see in the if the scale factor had been greater than 1, it would be larger and farther away. So in the last diagram we will see that the scaling factor by 1 by 2, so size was less. But if your scaling factor is more than 1, means it will become larger, so it will be larger and further away. So you can see that this is house is looking at small after scaling factor greater than 1 we are using, so we will get the diagram a larger one. So this is the scaling. So this is the scaling example. Now homogeneous coordinate, what is homogeneous coordinate? So a point xy can be rewritten in homogeneous coordinate as xh, yh, comma h. So the homogeneous parameter h is non-zero value such that y equal to yh by h. So we can then write any point x, y, hx, hy and h, means hx is homogeneous coordinate in x, then hy homogeneous coordinate in y. So we can currently choose h equal to 1, so that xy h becomes xy1. So high homogeneous coordinate we require. Mathematics commonly use homogeneous coordinate because they allow scaling factors to be removed from equation. So we will see in a moment that all the transformation we discussed previously can be divided as 3 into 3 matrices. So using homogeneous coordinates allows us to use matrix multiplication to calculate transformations which are extremely efficient. So homogeneous coordinates will in which we combine the geometric transformation into a single matrix with 3 by 3 matrix. So we will expand each 2D coordinate to 3D coordinate with homogeneous parameter. So after the 2D we go for the 3D transformation. So for this we require homogeneous coordinates. We are converting the 2D format into general 3D format by putting the z coordinate as 0. So combining geometric transformation into single matrix by 3 by 3 matrix. So we are expanding 2D coordinates into 3D coordinate by homogeneous parameter. So two-dimensional transformation matrix is x dash by dash 1 equal to 1 0 tx is a tx ty is a transformation matrix as this as translation or transformation as this factor. So in 3D we can see 1 0 tx 0 1 tx 0 0 1 x by 1. Two-dimensional matrix is this becomes in general form by using the 3D coordinate cos theta minus cos theta 0, sin theta cos theta 0 0 0 1. Okay. So two-dimensional scaling matrix is sx 0 0 0 sy 0 0 0 1. So in general form we are changing the this third coordinate as 1. Third scaling factor is 1. So what is inverse transformation? So inverse translation matrix is T inverse equal to 1 0. We are putting the minus sign in the Tx and Ty this transformation matrix factor. So T1 inverse equal to 1 0 minus 2x 0 1 minus Ty 0 0 1. Two-dimensional transformation matrix R minus R inverse is equal to cos theta sin theta 0 minus sin theta cos theta 0 0 0 1. So two-dimensional transformation matrix is S inverse equal to 1 by Sx 0 0. So 0 1 by Sx 0 0 0 1. So this is a translation basic to the transformation. So suppose you are getting the coordinate of the new translation matrix translated point. So you are multiplying the coordinate of the original image or original object by this translation matrix 0 f1 0 tx 1 0 1 ty 0 1. Similarly, we are getting a scale, then rotating, then shearing also. So we using the transformation matrix only we are getting the point of the new translation project. So in a nutshell, we can say that a transformation is a process that manipulates a polygon or other two-dimensional object on a plane or coordinate system. So mathematical transformations describe how two-dimensional figures move around a plane or coordinate system. So for transformation, there is requirement of a matrix that is called transformation matrix. So this transformation matrix varies from the operation to operation. For scaling, the matrix is different. For translation, matrix is different. For rotation, matrix is different. For sharing, matrix is different. For reflection, matrix is different. So only we have to remember the matrix format of matrix for each transformation. The matrix is different, and we can multiply some addition also done to get the transformated coordinates. Okay. Thank you for listening. All the best.